Good afternoon. Today we'll be talking about non-contact temperature sensors. So we will be discussing how to measure temperature at a distance without a direct contact with the object that you measure. First of all, we need to look into the physics that's behind non-contact temperature measurements. All the physics here and all the non-contact temperature sensors are based on measurement of radiation. So we look on the object, we measure how much radiation we receive from the object, and this is proportional to its temperature. However, there are many other effects that will complicate the measurements, and we need to take all those into consideration. So let's say we have an object and we want to measure the temperature of this object. The temperature of this object will influence how much this object will radiate, and this will be measurable in the emitted radiation. But if you have some ambient radiation, you may have some reflections from the object, and you may receive the ambient radiation directly to the sensor as well. So there will be some part of the ambient radiation going directly to the sensor, and some other part of the ambient radiation will be reflected from the object. And we will see with the sensor the sum of all those components that you see here. So we will not see just the emitted radiation as we would like to, but we will see emitted radiation plus reflected radiation. So this will be a problem. If your object is transparent on some wavelength at least, then you may see some heat sources that are behind this object. So you will see also some part of the transmitted radiation which will go through your object, and you will measure it with the sensor as well. And the last component that will be very important will be absorption in the atmosphere. So in the area between the object and the sensor, you will have something that will absorb all or at least some parts of the energy, and you will not be able to measure the emitted radiation directly. So today we will discuss all those parts here, and we will see what we can do with it if we want to measure correctly with a non-contact temperature sensor. We will start with the emitted radiation because that's the most important. That's what we want to measure. Emitted radiation, as you know from physics, is described by Planck's law. And Planck's law is basically giving us the dependence of intensity on a given wavelength as a function of temperature of the object. So what you see here is the amount of radiation that the object will radiate. And here you see the wavelength. And here we have different temperatures of the object. What you see here with the colors, it represents different temperatures of the object, and the higher the temperature of the object, the warmer it is, the brighter it is in the visible spectrum. And we see that the maximum point here of the emitted radiation is shifting with the temperature of the object. So if, for example, you have the object with 5,500 kelvins, which is roughly the temperature of the sun, then the peak wavelength is somewhere around here, around 500 nanometers. If the object is getting colder, then the amount of energy is getting significantly smaller, and also the peak of the wavelength is shifting to higher wavelengths. So here is red color roughly, and if the object is cold enough, we don't see it with our eyes. It is hot, but it's still hot. The reason why I'm explaining it here is that it has a very important relation to measurement of non-contact temperature. The point is that if you want to measure objects with relatively low temperature, let's say around 0 centigrades, 100 centigrade, so let's say normal room temperatures, the emitted energy is very far in the infrared spectrum. So for example, if you measure objects with 0 centigrades temperature, then 90% of the radiated energy is somewhere between, let's say, 7 and 50 micrometers. What wavelengths do we see with our own eyes? Roughly. I'm asking where are we in the spectrum? We are somewhere around here. So let's say we see from 400 to, let's say, 750 nanometers. So we see this part of the spectrum roughly. And if the temperature of the object is small, then we don't see it, but it will still radiate. This will have the effect that if I want to measure objects with low temperatures, I need to measure on different wavelengths that if I want to measure objects with high temperature. For example, if you want to detect some hot metals, you will be, let's say, around 1000 centigrades, and you need to have detectors and optics that will work in range between 1.5 and 7 micrometers. But if you are looking for applications with lower temperatures, such as 0 centigrades, you need something between 7 and 50 micrometers. So we will need to adapt the materials and the detectors for the specific temperature. Unfortunately, we don't have detectors that are able to work in the entire range, so that they are working from, let's say, visible spectrum up to the far infrared spectrum. So this is quite important, and we will also see that different non-contact temperature sensors will use different materials, and they will operate either on some specific wavelength, and this wavelength has to be adapted to the application. In all non-contact measurements, we need to know what are the properties of the object. And one of the most important property is called emissivity. Emissivity is a number that is saying us what is the radiation of our object compared to an ideal object that is called a black body. And a black body object is an ideal object that absorbs all the radiation it receives, and also it emits all the radiation that it receives. And we will compare the properties of our real objects with this ideal black body. Of course, there are some conditions under which this is working, and we will see that even in normal applications that you may encounter, it may not be true. So this is like an ideal object, but in reality it might be a little bit different. So the most important number that we need to know before we measure with non-contact temperature sensor is the emissivity of the surface of the object. Here in this table you have some numbers for different materials, and you may see that there is typically a wide range of emissivity where this is working. So the most problematic number in this application is how to get the emissivity from your object that you want to use. You can see that it varies in a very wide range. So an ideal black body has emissivity of 1. It means it receives some radiation and then it emits all the energy that it has received. Real objects, they do not work as black bodies, they work as so-called gray bodies, and they receive some radiation, but they emit a little bit less of radiation. Then the question is on what wavelength, and we'll see that a little bit later. Very close to an ideal black body is graphite or coal. So if you see some graphite surface, it's black, it's absorbing in a very good way the radiation and it's emitting it. So graphite or coal have radiation and emissivity that is typically very high. It's very close to the black body, let's say 0.97. On the other hand, metals that we have in industrial applications, they have typically a very low emissivity. So they receive some radiation, but most of the energy is reflected. There is also a relation between wavelength and emissivity. So emissivity is not a constant value, but it's a function of temperature, it's a function of wavelength, and it's a function of surface on the object. So you may have the same material, but if the surface has a different structure, you will have a different emissivity. For this reason, it's very hard to get the emissivity correctly for non-contact temperature measurements, and that's the biggest issue. Also, here we will use black body as a model, but remember that it is only an ideal model. So if we look on the real objects, they will behave in a different way. What you see here is the solar radiation spectrum of the sun, which we can model as a black body. But if we do this, we will have different radiation on different wavelengths, and this will not be in complete agreement with the black body model. So for example, here, this black curve is the black body spectrum as it would correspond to temperature of 5250 centigrades, which is the temperature of the sun, as we know. But here, this yellow area is what you measure above the Earth's atmosphere. And we can see that here in the visible spectrum, we radiate a little bit more energy that would correspond to the black body model for this temperature. And for example, here in the UV spectrum, we radiate a little bit less. So if we would compare, if we would say emissivity here with this easy comparison, let's say for this wavelength, then we would have emissivity higher than 1. But it's because we have not correctly interpreted the model. It's the black body is an ideal object from one material, and the sun is not from one material, for example. You can see also that there is a difference here around those areas. So here we radiate a little bit less than would correspond to the black body model. So in this case, we will be talking not about emissivity as a constant number, but we will be talking about spectral emissivity. And spectral emissivity will be a function of wavelength. So we will compare the wavelength, the amount of radiation between the black body model and between our real object on a given wavelength. And there will be a difference for different materials and for different temperatures, for example. The red part here is what you receive from the sun at sea level. And the difference here between the yellow and the red part is what is being absorbed in the Earth's atmosphere. So if I measure the temperature of the sun with a non-contact thermometer from sea level, I will be probably somewhere around here. I will receive less radiation, and it will appear as the sun has a lower temperature than it has in reality. And the same can happen in many industrial applications when there is something that is blocking the part of the radiation. This is typically an example of water vapor that you have between the object and the sensor. And even very small distances, when you have enough water vapor, can have a quite significant effect on what you measure. You can also see from this this chart that different wavelengths are absorbed differently. So for example, here you see that those parts are absorbed by the water vapor. So if I choose a detector that will measure the intensity of radiation on this wavelength, I will not receive anything, and therefore I will not be able to measure correctly the emitted radiation. So we will see that there are different types of detectors. Some work on one wavelength. For example, here 650 nanometers, and we are trying to compare the amount of radiation from my object on this single wavelength with the amount of radiation with some black body on some temperature. And some other detectors will work in the very broad range of wavelengths, and they will give us the total amount of energy that they receive. But in all cases, it's quite influenced with the absorption between the sensor and between the object. Also note that the black body model works well for large objects. When Planck has defined the idea of black body model, he has defined also the conditions under which this is working. And one of those conditions is that the black body, the object, is significantly larger than the wavelength. And for small particles, such as dust particles, it's not true. The dust particles, they may be similar in size compared to the wavelength. Let's say we measure on 1 micrometer wavelength, so 1 micrometer size is nothing unusual for dust particles. And if you have applications where you have those particles, then it may also have a significant influence on what you measure. The reason is that the small particles, when they have similar size to the radiation, they will influence the electromagnetic field around it. So let's say it can look like this. So we can imagine that those lines is the electromagnetic field around the particle. And this is what will happen. So it will seem as the particle has a much larger area, and the reason, the result will be that it will appear as the particle has a significantly higher emissivity than 1, because it is absorbing more radiation that would correspond to its area. And here, for small particles, you can find emissivities, let's say 5 or 10 or even higher. And then it's almost impossible to measure correctly their temperature. So that's another problem. Back to the absorption in the atmosphere. Whenever we want to measure with an atmosphere, we need to consider that there will be some absorption, and we can select a specific wavelength on which we know that the absorption is minimal. So you can measure in the shortwave infrared spectrum if the object temperature radiates enough in this wavelength. The wavelength is somewhere between, you see here, this is the visible spectrum, so this is roughly 700 nanometers up to, let's say, 2.8 micrometers. You can see that we still have some areas where we have significant absorption, especially for water vapors here. If our object is colder, we can measure in the middle wave infrared spectrum. We still have the problem with absorption, and some detectors are suitable for the long wave infrared spectrum, and we can use that to measure even colder objects. If you measure for higher wavelengths, then you typically have a problem with scattering, and you have problem with absorption as well. So for example, here above this wavelength, you have total absorption and scattering. So for longer distances, you cannot measure anything because everything will be absorbed in the atmosphere, and you will not get the radiation to the detector. Here are some examples of what is causing the absorption in the atmosphere. So it's especially water vapor that is absorbing all the energy. There are other components such as carbon dioxide or some other gases, but the most important component is water vapor. Now, regarding to the materials. The materials for infrared temperature sensors, they have to be completely different than for normal cameras. So even if we compare like a thermal camera and normal optical camera, the optics and the detector is completely different material. In the visible range, we are typically using CMOS chips for cameras, but we cannot use the same approach for the infrared detectors. And you can see that here we typically are using silicon or germanium. Those materials are quite suitable for infrared optics. And you can see in what range this works. So silicon works roughly between 2 micrometers and 10 micrometers. If you want to have different wavelengths, such as the long wave infrared window, you may use, for example, sodium chloride or some other materials. They may work in the visible wavelength as well, but it will have other disadvantages. For example, sodium chloride is normal salt, so it can get dissolved, so it's not very good material for an instrument. We'll now take a look on some pictures from the thermal camera. I hope I will be able to make it work so that you can see the image. So let's see if the thermal camera will work. So give me a minute to open it. For some reason I can't connect through USB to the thermal camera, but I will borrow it to you. You can take a look yourselves on the thermal image of something. And what I want to show here is some simple experiments. First of all, I will show you some thermal image of a metallic material, metallic sheet. It looks like this. This is steel, but that's not that important. And what you should see is, let me focus it first. Let me put it here. Can someone hold it, please, like this? I need a third hand so that you can take a look roughly on the image. What you should see here now is you should be able to see the reflection of you that is here in the metallic sheet. Do you see it here? Can you move it? Yeah. So you see, this is the reflection of you. So this is the reason why you have low emissivity here. So we have low emissivity. The most part of the energy that is received from you is getting reflected from the metal. But this is a function of temperature, and it's also a function of wavelength. So if I would measure on a different wavelength, we would see a different image. For example, we don't see that a good image in the visible range. So metals, they typically have low emissivity for larger wavelengths, so for the infrared, but they have relatively low emissivity for visible spectrum. So for us, we don't see a good reflection, but the camera sees a reflection. Now, stay here, please. If I would like to measure the temperature of this sheet, I cannot do it because I'm getting the reflection from all the ambient objects all around it. And even if I set the emissivity is 0.1, I will not be able to measure correctly the temperature. So the only possibility where I can get the temperature of this sheet is here on this sticker. This sticker has a defined emissivity. In this case, it's 0.96. And now I can read that on the sticker, it's showing me 25 centigrades. That's because here I have defined the emissivity of my object, and now I am able to read the temperature. I will pass you a second thermal camera that you may test yourself together with those materials, and you can test the reflections here. Also, I can show you different materials that behave differently in the infrared spectrum and in the visible spectrum. So, for example, this is a plastic sheet. I think it's like plexiglass. And here, for example, for us, it's transparent, but for the infrared camera, it's not transparent. We cannot see through it because it's blocking the infrared spectrum. So here, if I put my hand behind it, if it's in front of it, you see my hand. If it's behind, the infrared radiation is blocked, but the visible radiation is not blocked. You can do the same experiments with many different materials, like this one, like another sheet of plexiglass. It has the same behavior, so it's blocking the infrared radiation. If we take a look on normal glass sheet, here it's transparent, okay, but again, for the infrared radiation, it's not transparent. So I cannot measure an object that is behind an ordinary glass. I would need a different material, like a silicon or crystal quartz glass that will operate for certain wavelengths. On the other hand, here I have a black back, and this material is transparent a little bit for the infrared, but is not transparent for the visible spectrum. And this same case, can you hold this as well, please? You can point it on me. So here it's the same problem with this material, also plastic. I think it's like polyethylene, for example. So it's not transparent for us, but it's transparent for the infrared spectrum. So if I do this, for example, then you should see me in the thermal camera, but you will not be able to see me through your own eyes. So you can take this and you can pass it to them. So that's the problem with material and with the absorption. Another problem. Oh, I'm sorry. I will need the camera back, but you can play with the second camera. I will still need it. Another problem with infrared measurements is emissivity. Let's say I want to measure the temperature of this can, and if I take a picture of the can, even if I would know the emissivity of this surface, it's very difficult to get the reading, because here you can see I'm turning it, I'm seeing your reflection a little bit, and then at one position, let me take this can. Here you see I have placed some surface with a different emissivity. So if I would have hot water in the can, you would see a different reading on different surfaces. Although in reality, the temperature of the surface would be exactly the same. So that's the problem with emissivity. How can we work with that? We can use those stickers that have a defined emissivity. That's one option. Those stickers, they work to relatively high temperatures. I think they work something like 200 or 300 centigrades. So this is one option. A second option is that you use a special paint that you apply on the surface and that has a defined emissivity. So for example, if I want to measure the temperature on this heat sink, as you will do on the lab class, something from next week, the temperature should be the same around all the heat sink because it has a good heat conductivity, so there is no reason why one half should be warmer than the other one. If you look with a thermal camera on such a heat sink, when its temperature is higher than ambient, let's say 50 centigrades, you will see that here we have the 50 centigrades, but here on the aluminum surface, it appears like it has a low temperature, like 25 centigrades. And the reason is that we have a difference in emissivity. So here the black part is painted with a color that has emissivity of 0.96. You can see the stickers, so I can measure the temperature correctly on the stickers and on the painted area, but I cannot measure the emissivity on the original surface. So you can apply a special paint that works for temperatures up to roughly 800 centigrades. Another way how we can find the emissivity is that we measure what is the real temperature of the object, and we adjust the emissivity on the thermal camera to give us the same reading. So you can use a contact probe that looks like this, and this contact probe is nothing else than a contact thermometer. I'll maybe pass you this contact probe. It's a little bit larger. So here it's a contact thermometer. On this tip we have a thermocouple, and it is welded on a copper ring so that it has good heat conductivity. So for example, if I want to measure temperature somewhere, I place the contact probe and I read what is the temperature of the object. And now I can take the thermal camera and I can adjust the emissivity that I set on it to read the same temperature. So like this I can adjust back what should I read. Now the problem with all this is that I'm working with the assumption that the emissivity is not changing. So in other words, that my object has the same emissivity on all the surface. So this is typically true for objects made from one material with one surface type, but it's definitely not true in general. So for example, if you take a nice picture of a building, then you can compare the temperatures on a surface with one emissivity, but you can definitely not compare the temperature that you read on the building wall or on the window, because we have different emissivity, we have different material, we have different surface, we have different color. So it's very tricky to get correctly the reading with a non-contact thermometer, because you need to know emissivity and its function of temperature, its function of surface, its function of many variables. So the safest way how you can get the correct temperature reading from some object is really to paint it with this defined emissivity color, or if you are interested into some points only, then to place the stickers and you can read correctly the temperature at those stickers. Now related to detectors. I already told you that detectors are unfortunately not sensitive in the whole wavelength range where we would like to have them. So what you see here is a comparison of many different materials. And I just want to show you that different materials operate in different wavelengths. So for example, here you see we have germanium cooled down to 77 kelvins, and the peak of wavelength where it is the most sensitive is here around 1 micrometer. So if I want to detect very cold objects, I need a special detector that will be cooled down, and it will work in the best way around this wavelength. On the other hand, for example, if I take an alloy of silicon and gallium, cool down to 4.2 kelvins with liquid helium, it will have a peak sensitivity around 15 micrometers. So it will be good for detecting very cold objects. But on the other hand, you see here that this sensitivity is around 5 orders of magnitude smaller. So I need to adjust the detector and the optics based on my application. If you go and buy a thermal camera, they will ask you in what temperature range do you want to use it. If you want to use it for 500 centigrades, or if you want to detect some bodies in a forest that will have like 20 centigrades or 30 centigrades. And you need to make a choice in this sense. You can also see that there are some detectors here, and their sensitivity is a straight line. It means they can operate in a wide wavelength range. One example is the thermistor, or called a bolometer. We'll discuss that as well. And the second example is a thermocouple here. We already know a thermocouple from last week. So they really work in a wide range of wavelength. That's fine. But you can note that here we have a very low sensitivity compared to the other types. So, for example, here we have 10 to the power of 8, and over there we have 10 to the power of 14. So we have like 6 orders of magnitude in sensitivity, which can be very significant. So we will discuss also how those sensors work. They are typically used in simple non-contact thermometers. So they integrate the energy that we receive, but on the other hand, we cannot use them as thermal imagers because they are not that sensitive as the detectors that work around those wavelengths and sensitivities. The first sensor that we will discuss is based on this picture. This picture is saying me that, for example, if I look on one wavelength, I can compare the amount of radiation that I receive. And from this amount of radiation, I can say what is the temperature. So, for example, if I would look for 650 nanometers, I would be able to tell if this is the temperature, or if this is the temperature, or if that is the temperature. So I'm comparing one wavelength only, and this is called a pyrometer for a single wavelength. In other words, it's also called monochromatic pyrometer. The one example that I will show you is called a disappearing filament pyrometer, and it is a device that is used especially if you want to measure in a furnace, because here we are using our own eyes to compare the intensity of the object with the intensity that we have available at the sensor. And since we are comparing this with our own eyes, we need something that is in the visible range. And our eyes are most sensitive for red color, so we are using 650 nanometers, which is red color. How does it work? We look on the hot object, and we focus the light from the hot object. Here there is a lamp with a filament, and we are comparing the brightness of the object with the brightness of the filament. And if on one wavelength the brightness is the same, we can say that the temperature is the same as well. That's related to this. So the brightness, if here I measure the same brightness for the filament and for the object, the temperature has to be equal. So if we look into the device here with our own eyes, we are not looking directly on the object through the lenses, but through a red filter and through a gray filter that will decrease the intensity from the hot object of the radiation. And here through the red filter, this red filter will filter out all the colors except the red color around 650 nanometers. So what you see in the instrument is something like this. You see a part of the object, and then you see the filament. We can adjust the temperature of the filament by simply changing the current. It's like a bulb. It's called a pyrometer bulb. And from a normal bulb, if you change the current, you change the brightness. So if the temperature of the filament is higher than the temperature of the object, then you see a bright filament on a relatively dark background. So you see something like this. And we know that this is not correct, because if the temperature is the same, we have the same color. On the other hand, if your filament is colder than the object, you see a bright background and you see a dark filament on top of it. So we don't want this either. We want that we have the same radiation, which means that we see something like this. We have a hot filament and we have the same temperature from the object. So in fact, the filament disappears from the background. That's why it's called a disappearing filament pyrometer. So we are adjusting the current from the bulb until we have this result, and then we read from the scale what is the temperature of the filament. Of course, the temperature does not need to be the same. Here you see that we have a neutral filter. So with this, we filter out some part of the radiation. A neutral filter means that it's decreasing the intensity independent of the wavelength. So here we decrease the intensity of the radiation. That means that here the filament of the bulb can have lower temperature. It will not melt. So for example, if this is a furnace, we see that we have melted iron, and here we don't need such a high temperature. This is all accounted for during the construction of this filament pyrometer. So it looks like this. You see here, you point that through a window into the furnace. You look into this eyepiece, and here you have a scale calibrated directly as a temperature. And here, typically with the ring, you can set what is the current in the filament. So you just look through it, you wait until you have this situation, the filament disappears, and then you read from the scale what is the temperature. You will have a chance to use this on the lab classes. So this principle is comparing a single wavelength. A second option would be if I measure somehow the total amount of radiation that I have received on a detector. This principle is called total radiation pyrometer, and it's typically using thermocouples or RTDs as the sensors. As we have seen from the detector chart over here, the thermistor or thermocouple has a nice sensitivity for different wavelengths. So I can focus the radiation incoming from the object on this sensor, and I can measure what is the temperature of the sensor. So the total radiation pyrometer then looks like this. This is the sensor itself. So it's either a thermocouple or an RTD. Here you have a set of lenses and filters that focus the radiation on this detector. And here you have the object with the temperature that you want to measure. So the radiation is focused here on this detector, and if the object temperature is higher, the amount of radiation will be higher, and we will be able to read it from the scale as an increase in temperature. Now the part on the red, you don't need to have it in all cases. It's allowing you to focus the optics and to point it correctly on the object. So you may just have this part and this part with the sensor. Here are some examples of those devices. So they look like this. Here, of course, the optics is not from glass, but it's from appropriate materials, as we have already seen. Here you see some application where they used it to measure the temperature during an explosion of a charge. Now, the typical application looks like this. So you have a glass, you have metals, and you want to measure what is the temperature during the manufacturing process in different steps. In all those applications, it's very important to keep in mind that emissivity is a function of temperature. So if you measure, for example, glass, you need to select with this filter a specific wavelength on which you measure. Because if you cannot measure it in the entire range, the emissivity is a function of temperature. And it's quite significant. For example, for metals, the emissivity, if you have here the temperature, wavelength, and here you have emissivity, then typically for metals it is looking like this. So, this is metals are like this. So they have low emissivity for low wavelength, and they have higher emissivity for higher wavelengths. For different materials, it may look, for example, like this. So they may have emissivity that is low for larger wavelengths and high for small wavelengths. Also, there is a function between temperature and emissivity. So if you are looking for a specific temperature, you should change the emissivity during the measurements. I will not show any specific charts here, but it's quite significant. For example, you measure with emissivity of 0.8, but if the temperature is changing from 1000 Kelvin to 1500, the emissivity may drop from 0.8 to 0.5. And this will give you a different reading in what you get from the non-contact temperature sensor. Okay, let's take a look on how those devices work, how infrared thermometers and thermal cameras work. We'll start with the simple devices, which will be the infrared thermometers. Now, infrared thermometers, they work like the total radiation pyrometers. So we measure the amount of radiation with a temperature sensor. So for example, it's a thermocouple or a bolometer, which is the same element like in thermal cameras. And we focus with lenses the radiation on a detector. But this is a single point. This gives me a single reading. So it's not a matrix of points. What is very important is how to measure correctly with those devices. Of course, I need to know emissivity. That's the most important problem. But even if I know correctly emissivity, I need to be very careful how do I measure with the IR thermometer. All IR thermometers have a field of view, so it means that they do not measure in a single point. For example, if I take this thermometer, I turn it on, you see those 3 dots, and those 3 dots represent me the field of view. The central dot is the center, and the 2 dots on the sides, here and here, are representing a circle. Where do I measure? So I'm always measuring in a circle. So let's say I know the emissivity of the wall, so now I'm reading 22 centigrades, for example. The field of view is a function of distance, and for infrared thermometers it typically is looking like this. So it's a cone, and normally you find a description based on distance and between the diameter of the circle. So this is an example you may find in a manual. They say it's 6:1. So it means that if you are in the distance of 6 meters, then the diameter of the circle where you measure will be 1 meter. It may be a little bit different. The infrared thermometer may have some optics, so it may decrease with increasing distance, for example. What you need to consider is that the field of view needs to be completely covered with the object. So, for example, if I measure on the wall, then that's fine. I read 22 centigrades. But if I do this here, I measure part of the wall plus part of the plastic cover. And they definitely will not have the same emissivity. So I'm measuring something between the temperature of the plastic cover and temperature of the background, which is the wall. So the best option is that the object is larger, significantly larger than the field of view. Then you measure correctly. For example, of my hand, like this, then this would be fine. The object is larger than the field of view, and now it reads 33. I didn't set emissivity, so I don't know if it's correct. But if I do this, here I will read something different. I'm reading 30. So I'm reading the sum of the background radiation plus some part from the object. Now, what you see here is incorrect. So the object is smaller than the field of view, and this means that I'm getting something between the 2 correct temperatures. The situation that is shown on this picture can be correct as well. It means that the field of view is the same size like the object, but here it depends on the object material and on many other conditions, such as if the temperature of the object is the same on its its entire surface. So if it is a good heat conductor, then we can assume that it has a good heat distribution of the temperature on the surface. So this may be correct as well. But this is not correct. We see that the object is smaller than the field of view. It works in a similar way also for thermal cameras. But thermal cameras, they give you a matrix of points. So thermal cameras, they have a set of temperature detectors. All the light, all the radiation is focused on those detectors, and we receive an image. The most common sensor for thermal cameras at least for the ones that you will see in our labs, is a microbolometer. A microbolometer is nothing else than an RTD. So it's a resistive temperature detector that is very sensitive, and it changes its temperature as a function of the radiation that it receives. So it is looking like this. This is the sensitive material. That's the pixel. The pixel size is a few micrometers. So, for example, 10 micrometers pixel size. And you see here that we have those terminals, and those terminals are used to measure the resistance of this surface. So if there is some radiation, it will increase the temperature of this surface, and it will change its electrical resistance. Now, the changes in temperature are very small, so this area is insulated from the substrate material. So that's why here there is a gap, and here you see there is also a mirror that will mirror back the radiation that went through this surface, so that we have a higher sensitivity. All those elements are arranged in a matrix. So it typically looks like this. This is a picture under a microscope. You see the pixel size here. This is 10 micrometers. So let's say in this case, it's like 40 micrometers squares. And there will be few, let's say 100,000 or 200,000 pixels on a single chip. So the single chip then is placed at the focal point of a lens. Here we have a lens that will focus the infrared radiation. We already know that the lens needs to be from a different material than glass, such as silicon or germanium, for example. And we read out the different temperatures from different pixels, and this will give us the thermal image. The bolometer typically looks like this. So this is the chip itself. This is the sensitive area. You see the terminals to read out the pixel values, and then here the electronics that is associated that will give you the video signal or photos. And here you see it's covered with a lens that will focus the light. Just by looking on the color of the lens, you can say that this is definitely not glass. It's typically silicon, which is this shiny material on this area. We cannot see through, but it's transparent for infrared radiation. And then, of course, the thermal camera looks like this. We have a chance to play with it, and you will have more experiments on the lab class. Now, how to correctly use it? Of course, we need to know emissivity. If we don't know emissivity, then we cannot measure temperature. A thermal camera is a good device if you want to measure temperature distribution on one object that has one emissivity. So it can give you an insight into a wall, for example, and you can see breaks, you can see if there are some problems with insulation, because it will give you different temperatures. But it's definitely not a good idea to take pictures like this, because they have objects which have different emissivities. And it will look like it has different temperature, but this may not be true because it's just caused by different emissivity. What you see here are different surfaces. This is metal, this is wood, and this is snow. So here, this is a picture that I took. Here, I verified with the contact probe that the temperatures are the same, but because here the metallic part has a different emissivity than the wooden part and then the snow here, it is looking like it has a quite different temperature. You can see the difference here. The metallic part shows like -7, the snow part shows like minus maybe 15, and the wooden part is somewhere in between. So if you take pictures of buildings with a thermal camera, you cannot read the temperatures, but you should look for temperature differences on objects which has different emissivities. So that's the basic problem in pictures like this. You don't know what's the emissivity. The second problem will be related to reflections. So if you are looking on some metallic surface which has low emissivity, a significant amount of radiation will not be from the object, but will be reflected from somewhere else. So here you see that's me in a mirror. And if you want to measure the temperature of the mirror, you cannot do that because you're measuring the reflection of yourself in front of the object. It's the same like if you play with the metallic sheet, you will get reflections of all the surrounding, but not from the material itself. So what you can do here is you should apply the stickers, or you should paint the surface if you want to get the emissivity correctly. Now some examples of applications where you can use thermal cameras. For example, you can measure sediments in tanks. Now all this assumes that you are looking on a surface which has roughly the same emissivity in the whole surface. So for example, this is the tank, and here on the bottom we can see that there are some sediments in the tank, and we can see them because here we assume that this has the same emissivity and it will radiate less because the heat is blocked by the sediments that are on the bottom of the tank. Similar example is if you detect some faults in machinery, such as bearing overheating. So you look on a motor, on an induction motor for example, and you may see that something is happening here. So you see that there is a problem, but it's not supposed to give you temperature. You cannot read temperature from this image because you don't know if the emissivity is the same. If the motor would be painted with the same color all around its surface, then you may say, okay, I have a same surface, and then I know the temperature here is 50 and temperature here is 20, for example. But those images, they show you that something is happening, but you cannot use them to get the absolute temperature readings. Similar application if you want to detect heat leakage under some insulation or some leakage from a pipe, then you may see images like this. You see, okay, that's the object itself. Fine, I assume that it has the same emissivity on the surface, and I see that there is something happening here. It has a different temperature, and since it has the same emissivity like all those surfaces around it, I may say, okay, really is something happening. If this would be a metallic pipe, then you should look also for other heat sources that may be in this area, like this. So this may not be a leak, but it may be a reflection from some other pipe that is nearby, or from some other machine. You can use thermal cameras in electronics. So this is an image of a printed circuit board. You see here different chips, and it's looking like here we have a problem because it's quite hot. So either the chip is faulty or we have some short connection. Again, unless we paint this printed circuit board with the defined emissivity color, we cannot say what is the temperature. So this assumes again that all the surfaces in the image have the same emissivity, which definitely is not true. Fortunately, many materials, they have emissivity very close to the 0.95. So it's not that dependent on color. So for example, if this is green and this is black, it may not have a significantly different emissivity. But it's a function of material, and if you really want to be sure that you read the temperatures, like absolute readings, then you need to paint it with the defined emissivity paint. Some applications at the end, and this relates to the absorption of IR in water vapors. For example, there was one application, this was done in Germany, and this was done here. The goal was to measure the temperature of disc brakes with non-contact thermometers. The reason to do this is they were doing a race, and they wanted to verify the temperature of the brakes during this race. So normally, how it is done is that you have this, that's the disc in the brake, and they are using thermocouples. But you need to maintain the contact between the disc and the thermocouple at all times when this is turning. So the idea was to replace that with non-contact sensor. And the problem here was that they used water cooling of the brakes. So here you see that's the brake itself. This was the sensor. The distance between the sensor and the disc brake was like 3 centimeters roughly. And everything worked fine until they start cooling. So when there was no water vapor, no cooling, then the reading was the same like from the thermocouple. But even on those 3 centimeters, when they applied water to cool it down, it created such a huge amount of water vapor that it blocked the infrared radiation. So here it turned out that it's not a good idea to use those IR sensors, at least on those wavelengths, without any extra air, so that here we need to keep the environment clean between the sensor and between the disc brake. So this may be an example where even very small distances may cause you trouble in IR reading. At the end, let's watch one video how to use non-contact measurements in glass production. You will see the entire glass production line. It's called float glass because the glass is floated on a molten tin bath so that it's quite flat. And you will see that there are many non-contact sensors in the application that give the control over this process. So here you see the float glass line. This is the furnace where they melt the glass. This is the tin bed, so it's a molten tin, and the glass is floating on top of the molten tin, so it becomes quite flat. And here you see the pyrometers that are installed at many places of the production line. So they measure the temperature in the furnace, they measure the temperature between the tin bed and between the furnace, and then during different operations in the process. So here you see many stages all around the process that uses those sensors. So this is the area where it cools down, so it's dragged on from the tin bed, and it's gradually cooled down here. And at many places you need to measure the temperature, because if you cool it too quickly it will break. If you cool it too slowly it will not have the defined properties. So this is an example of a line scanner. So it's basically a thermal camera, but it gives you a temperature profile in line. So they are able to measure if the temperature is uniformly distributed in the entire product, in the entire sheet of the glass. Maybe I'll just open the second video and I will just go to the time when you have the sensor visible. So what happens here, they describe the whole process, including the temperatures, but at specific points in the production line you need to verify if the temperature profile is correct. So what you will see in a few seconds is the line scanner that is reading the glass temperature. It looks like this, and the output of the scanner is a temperature profile. So we will see it looks like this. It's installed between the conveyor belts, so it's installed here in this position, and it's looking from top to onto the glass, and it's reading a line. Since this is glass, it's transparent, and you need to use filters for a specific wavelength. So you cannot measure total radiation, but you measure radiation on a specific wavelength only. And the result looks like this. So you see basically the temperature of the whole sheet, and you see, okay, it's fine, or it's uniform, or it's not. We eventually need to discard it. Any questions? No questions? Okay.